Alright, time for another draft physics.com, debatephysics.com, also video presentation. Alright, so I just already did this, so there's drawing on top of my drawing, which is not very good. But anyway, so in the last video I did make a statement concerning what shenanigans they did in the video in terms of not letting you see the whole pattern. So what they showed you, I should do this in another color. They showed you an image that looked like this little bar pattern, and they called that the double slit pattern. So obviously that isn't this classic pattern, okay, of dots, then nothing, then dots, then nothing, then dots. And the reason is if you make the slits infinitesimally thin, you basically are just saying you have 2 point sources with an open slit, but if I close the slit very, very tightly, these 2 point sources end up being the same location. I can't draw a line from this one and a line from this one to some location and have a wavelength of difference in the length of the line. So I can't create any nodes. So with a very, very thin, an opening less than a wavelength, this is all the pattern you'll see. And he showed that when he covered one slit. Now what he should have done is cover the other slit and mark the location of the first blob, and you would have seen that the second blob would have been right on top of it. Because they always try to say that there's two blobs, you know, that somehow when you close one slit, one blob's over here and the other blob is over there, and it's not. They're right on the same place because there's only a tiny difference in the distance between the two slits. But anyway, the infinitesimal opening means you're basically taking a 4-source experiment, you know, 4 dots separated, and you've turned it into a 2-source experiment because the dots are so close to each other that they can't create a difference. And so all you have is the one distance again. And so the one distance can only happen inside that blob. It can't happen anywhere else because there's no contribution from the openings to put little lines inside of. All right, so it wasn't that they didn't show you the pattern; it wasn't created because they have essentially taken a 2-slit experiment with 4 individual point sources and turned it into a 2-source experiment. Alright, just want to make that clarification. So you did get the odd number, okay, and it's basically inside of the 1 maxima, because say if they had a little tiny bit bigger slit, say just 2 wavelengths, well then you would have got the double maxima and you would have got one more maxima, and then you would have had lines here and you would have had lines here. But because they had it so narrow, you didn't get anything on that arc except one blob. Alright, that's probably enough of an explanation. I did draw the vector lines, you know, so if you tried to go to this location that wasn't showing, I'm just saying you can't draw 2 lines. If I make these 2 openings, 2 slits, 2 surfaces so close together, I can't draw a vector to any location where they will be a wavelength of difference in the length of the lines. So obviously I can't have a interference pattern. Alright. I can't have in phase, out of phase, because there's no back in phase again. It never makes it to in phase again. Alright. It can never reaches beyond a wavelength of difference. Alright, enough of that, I think, and such. So we'll go back to the video. Alright, should be okay to play.
We're going to do a microwave experiment now, which will be directly analogous to the Young's optical interference experiment you saw just a little while ago.
Okay, so
I want
it
to buy your
won't be.
house. I can pay you.
Shit, damn it. Right, so back. It won't be directly analogous, so I'll draw a picture of how it's different. Alright, should be back. Okay, so in the slit experiment, my argument is basically that that the surfaces are breaking the photons. Okay, the photons aren't being stopped or killed. They're just being disrupted by the surface. So the photon comes in, if it goes near the surface, pieces of it break off, all right, and are scattered. Okay, and that the scatter from those surfaces hits the target, and there's a 50-50 chance, okay, that it's going to be going in phase or out of phase based on the distance. All right, now in the radar experiment, there's just two cones, essentially, and you could do the radar experiment in this exact configuration, where one's over here and one's over here, and you could put a receiver here and move it back and forth, and you could get on, off, on, off, on, off. What would be a fringe pattern, but there's no, it's obviously not being created by the same mechanism, because it's about what the receiver's receiving, not about what's being interfering in space. That is, there's this wave, if it was a wave, isn't interfering with this wave if it was a wave. They're not coming from the same side, and therefore interfering with each other by crossing each other. That never happens. So there can't be any idea of the waves interfering in the classic drawing of wave interference. It doesn't happen because they're coming from opposite sides. And what it's really about is just the receiver, okay, is sensitive. And so this radar experiment, there's no four surfaces. Okay, there's just the two signals. And the fact is the signal and the receiver. The only thing you're messing with is the fact is the receiver can't see out of phase. So you're basically saying, if I send the signal out of phase, the receiver will say, I can't see it because it's jammed. So it's essentially radio jamming. So if I had two radio stations and they were broadcasting equally, I can do the same thing. I mean, you could probably have experienced this in the old days, if you were alive anyway, where your car radio keeps going in and out because there's two competing radio stations on the same frequency, and basically your radio's tuning into one or the other, but it can't tune into both, and that's the trick. So if they're at all out of phase, the problem is the radio can't decide which one to tune into. So it's getting 50 megahertz here and 50 megahertz coming from someplace else. And if they're out of phase, it can't see either one. And if they're in phase, then it can double. It'll hear both of them. So that's the difference here. This is all about the fact that our receiver can only receive in phase. And as soon as there's two signals that are out of phase at the same frequency, it fails. So there's a thing called a klystron that runs these things, and those things are very specific, and they vibrate. So what they're really doing is it's an idea that you're creating a resonant frequency and it vibrates. Well, you can get the idea that if I have one signal that's telling it to vibrate this way, and the other signal is saying at the same time, vibrate that way first, you could see how, well, that won't work. It won't vibrate. So it can only vibrate based on one of the signals. If it tries to be pushed by both of them, nothing's going to happen if they're out of phase. But if they're in phase, that is, if this one is pushing this way while this one is pushing that way, relaxing. So if they're both in sequence in terms of the direction they're pushing the object, then it'll vibrate. But it can't vibrate if they're both saying push and the other one's saying push at the same time. So I guess it's the other way around, right? You're basically saying when they're in phase, there's no signal. And when they're out of phase, all right, then there can be a signal because both of them, one will be pushing that way when the other one is pushing that way, essentially. relaxed, let's say, not pushing. And then the other one will push when the other one's not pushing. So then it can vibrate. Alright, so it's a clear distinction. So this is not the same experiment in the sense that you don't have, it's not a four-source experiment. You're not going to get the two patterns. You're not going to get an envelope pattern. And so it's and you're not going to get the double maxima either. So it's a very different experiment. Not analogous is the point. Not a perfect analogy by any means. You're testing for a different thing. You're testing just about the phase, and it's because your receiver can only receive one signal when they're out of phase. When the two signals are out of phase, it can only vibrate to one of them. Ooh, I didn't need to hit that. I believe I said that correctly, but who knows? It's always the backwards or something, but I'm just saying it's clearly a different experiment in the sense that the receiver is the limiting factor. It can't see when it's jammed. So this is really just about signal jamming, not interference.
The waves will have a frequency of 9,000 million cycles per second, corresponding to a wavelength of about 3.3 centimeters.
Right, so Brozo, okay, when I first met him, did some of these experiments, so we did learn a lot about how it actually works.
We'll produce the microwaves in a tube called a klystron. Here's one.
It's basically a diode of some kind, and again, it only vibrates at that 9,000 megahertz kind of thing. It doesn't do anything else. So any other signal, the harmonics can cause it, but it has to be a harmonic, of that number. So it's pretty limited in its function. It doesn't pick up any frequency, just that specific frequency.
Microwaves come out from this antenna. We pump electric charge or current up and down this antenna, and the accelerated charge sends out the waves. We've got the same klystron in this metal can. The accelerated charges on the antenna start an electromagnetic wave down this pipe.
So it's kind of funny that they funnel it through all of this crap, frankly. But whatever, it does travel, so it works.
The wave reaches this point and splits and arrives at these 2 points with identical phase.
So obviously you could just use two klystrons that were stimulated simultaneously. So this is like using two antennas, or you could just produce two signals. This ensures that you're using exactly the same signal and it will be on exactly in phase with each other. So they're basically just taking it, making the sound, if it was a sound, putting the sound out of the two speakers to be sure that the two sounds are exactly in phase when they start.
We then feed them through these two horns out into space. The purpose of the horns is to minimize reflections, which are caused when we make the transition between the pipe and the space.
So when he says minimize reflection, it just has to do with the forcing it in a direction, frankly. But I don't think it really minimizes reflection.
The two horns in this experiment will act just like the double slit did in the optics experiment.
So it really has nothing to do with it. It will not create two surfaces. So there's no surfaces here. The horns could be round, they could be any shape. It doesn't have anything to do with it.
Here we have a detector which is sensitive to the resultant electric field tangent to it. We're going to move the detector back and forth through space this way, thus sampling the total electric field resulting from both these horns at each point in space.
So again, if they had the two horns, okay, producing the same signal from opposite each other instead of parallel, instead of shooting together, one was here and one was here and they were pointing at each other, you could do the same thing by just moving it in between. You'll get on, you'll get off, on, off, proving it's just about phase. There's no interference. It's just they're in phase, they're out of phase, they're in phase, they're out of phase.
The output of the detector will be fed to this meter. Now let's do the experiment. As I move the detector this way, across the incoming waves, you can see that the deflection on the meter goes through a series of maxima and minima.
Right, so this is just in phase and out of phase, and there's only two sources. So it's not a double slit experiment. It's back again to being a single slit, two source experiment. Single slit, two sources, two surfaces.
You can also hear it on a loudspeaker we've hooked up because we're chopping the microwaves 1,000 times a second.
And so again, this whole wave theory again breaks down to some extent again when you recognize, well, if these were real sound waves, then it should be just as loud over here as it is here as it is over here, and it's not.
Just as in the optics experiment, when a crest from one horn meets a crest from the other, we get a constructive interference or a maximum at the detector. And when a crest from one horn meets a trough from the other, we get destructive interference or a minimum on the meter.
So it's exactly the opposite. When the two are out of phase, there's no signal because it can't choose which one to vibrate to. And when they're in phase, that is, they're both throwing a bit at the same time, then yes, they can. It's loud because they're both in phase. They're both pushing on a surface. If it was pushing, they're pushing at the same time, so it's going to wobble. But if one's pushing and the other one's pulling, so to speak, obviously it can't wobble.
In order to show that this is really an interference phenomenon...
Oh dear, so this is the part where okay, well, we'll play it.
We have to show that both horns are simultaneously involved in producing the resultant field at the detector. Now you'll remember we stopped at a minimum.
Okay, so the point is now he's taking a place where there's no signal. Now we know both the horns were producing, but there's no signal. So now he's going to block one of the horns. So the jamming horn, either one could be called the jammer. Now he's going to block the jammer. And obviously the horn can now be heard, the other one, because nothing is jamming it.
Let's close one of the horns and see what happens. The intensity on the meter went up.
Right, so he's at a minima, and now he's turned a minima into a on. So he was at a point where it was a very low signal, and now it's getting a very high signal because he blocked the jammer.
This means that the field from this horn can no longer cancel the field from the other.
Jam.
Let's go back to a maximum. And I'll again close one of the horns.
So closing one of the horns, the signal's still there because the other horn still works just fine. So again, if you block one of them, the other one still works just fine.
In this case, the intensity on the meter went down. This was because we closed one of the horns, thus leaving only the intensity due to the other one.
Exactly. So all you're doing is proving that you can jam the signal.
It's easy to show that microwaves can be polarized.
You can't jam them when it's in phase. You can only jam them when they're out of phase. So when they're both in phase at a location, you're not jamming. But as soon as you put your signal out of phase, that's when you jam it.
Place a screen like this between the horn and the detector, you can see that in this position the intensity on the meter is relatively unaffected.
So the antennas are going this way, the bars are going that way. So it's not like the signal is the frisbee flying through the bars. It's the signal that has a polarization this way is somehow going through bars that are against its. So it's like trying to take the frisbee and put it through the bars that are going up and down, and your frisbee is horizontal. And you're saying, well, that can't happen. So the trick is again, the fact is these little lines are going to be distortions that are going to cause the photons. Okay, it's radar. They're photons. Okay, it's going to cause them to move a little up and down. So your signal is going in this way, and it's going to be disturbed a little bit up and a little bit down. So it's really easy for that to be fixed in the sense that all I have to do is make it go back up or make it go back down, and I've restored the signal. And if I had distorted it, the thing going through this way, if I had distorted it this way and that way, well, that's harder to put back into that orientation. The distortion is not in a favorable direction.
But if I rotate the screen by 90 degrees, the intensity on the meter drops almost.
So that's the part you're saying, wow, the stuff going this way can't get through the fence. And of course it should be able to go right through the fence, but it can't. And but the reasoning is because if the point I'm making to you is this is a stream of photons, one bit here, one bit here, one bit here, running parallel into you. Okay. And if I scatter them this way and that way, I'm going to have an awful hard time putting them back together.
To zero. The reason for this is that in the second position, the electric field was parallel to the wires. This set up strong currents in the wires, which converted...
So there's absolutely zero evidence. So they never put detectors on this wire to see if it's collecting energy, ever. So they're just telling you of a theory that somehow the signal got absorbed by the wires. It didn't. There's no evidence. Just like in the polarizing film, it doesn't get hot, it doesn't melt, it's not absorbing the photons, it's just disturbing them, breaking them, frankly. And then they can be remade.
Much of the microwaves to heat.
So no evidence of this heat, no evidence that happens. The little holes in the door of your microwave oven, there's no evidence they get hot. They're doing essentially the same thing. Okay, they're breaking the big photon in the sense that, well, I guess I really should draw this part. Really should. Alright, so the microwave signal, I'm just arguing that all these photons look the same way. And let's just say you had some red light. So red light, I could draw it like this and say, okay, the frequency is much smaller. Well, it's 1,000,000 times. It's 1,000 times smaller than this distance. Okay, you're talking about 500 nanometers here, and you're talking 3 centimeters here. So it's a huge difference. But anyway, and what I basically pointed out was the polarization is just the idea that this is a signal that's initiated over a period of time. And so you're saying a bit of energy is launched and it goes on its way. At the time this second bit is launched, right, so the electricity goes this way, the second bit is launched, this one's already halfway here, right, when this one just starts. And then when this one starts, this one is halfway, and this one's this way. So you can understand that they're moving through space parallel to each other, all in the same direction. That's the polarization. The lead one here, then the second one, then the third one, with a little bit of distance this way, and a frequency this way. Alright, and so what you're saying is when it's going through the polarizing device, that this distance is changed. So instead of changing this way and that way, You're just changing that this one's a little higher, this one's a little this, and this one's a little that. So you've changed the polarization, but you haven't, the distance of the polarization, but you haven't changed the frequency. So the frequency's still okay, but you have changed where they are in space, and you're also giving them, it's obviously an angle change. And so, but the point is you could use another device to restore the photon's function, its pattern. You can put it back to the same pattern again. You can reconstruct it a lot easier than if it had spread this way. I think that would be good enough to explain the point. No. And continuing.
In the first case, the electric field was perpendicular to the wires. Not much current flowed in most of the...
So, just this whole idea, they're claiming a current, they're all this, and there's no evidence that any of that happened. So just like with a ballistic pendulum, and they say there's a bunch of heat in the pendulum, they never measure any of it.
The microwaves got through. You have noticed that in this experiment, the microwaves were already polarized as they left the horns. The important thing is that we could polarize them, just as we were able to do with light in the optics experiment.
So we know all of those radios type signals are always polarized by the antenna. So you could call that antenna polarization, where photons come out at all kinds of polarizations because they're just being polarized by which way the energy, the electricity tends to move through the material. And you've seen lightning zigzag all over the place, meaning that obviously the electricity doesn't necessarily travel in a straight line.
And once they were polarized, they retained this property as they traveled through space. We showed you this when we placed the screen at some distance in front of the horn. This meant that the microwaves had to carry their polarization property with them as they traveled to the screen. Incidentally, it's easy to measure the wavelength of microwaves. If we place a reflecting screen behind the detector, we can pick up a standing wave pattern. And by measuring the distance between minima, we can get the wavelength of microwaves.
So all you're doing when you're reflecting from another distance is creating a second signal. And so you're just going to jam it inside that reflection, and that'll tell you the distance.
Waves. Let's go do it.
That'll tell you the frequency, how far apart the pieces of energy are.
In back of the antenna. The wave coming out of the horn comes down this way and bounces off this plate. At the position of the antenna...
So we know that doesn't make any sense at all. What's happening is there's microwaves going right through the back end. They're going to reflect off the plate and then come out in sequence with the horn ones. And so when they're in phase and when they're out of phase will just be dependent on that distance of the reflection. So you can just move that reflector in the back and you can tell when they're in phase, loud signal, out of phase, no signal, less signal.
We have both an incoming wave and a reflected wave. As you know, the sum of two such waves gives the standing wave. I'm going to move the antenna in this direction and follow its position with this pointer. In order to allow me to measure the standing waves, I'll put this centimeter stick behind it as a scale. As I move the antenna, we go through...
So obviously it's twice the distance, right? It has to go back and then it has to go forward. So it's, if you read, yeah, if you read 0.75, then you know it's 1.5.
A minimum, maximum, and let me stop at a minimum and mark the scale. Now I'll move the antenna to the next minimum.
A centimeter and a half, I think. Yeah.
And mark the scale again.
Yeah. So 3 centimeters.
The difference between these two marks is just 1.65 centimeters. As you know, standing wave minima occur every half wavelength. This means that the wavelength of these microwaves is twice 1.65, or 3.3 centimeters.
And it's twice because it has to go
The
back.
most common use of microwaves, radar, is probably familiar to most of you. In radar, we shine microwaves onto an object and measure the time it takes for the microwaves to go to it and come back. If we take half this time interval and multiply it by the speed with which microwaves travel, we can calculate the distance of the object. This speed turns out to be exactly equal to the speed of light.
Right, so we know that all the photons are the speed of light. Electricity, almost. Magnetism, speed of light. Gravity, speed of light. So it's really the speed of force. It's kind of irritating that, I've been saying that for 10 years, and it hasn't caught on at all. Like, okay, let's all just concede it's the speed of force. We really should say it's the speed of force. That all of the discrete tiny stuff moving very fast is all moving that same speed. So it's kind of silly not to call it the speed of the elemental force that exists in the universe. And that's all you're really doing is reflecting it. The force is already in the universe. The little bits, the little sisyphuses. And all you can do is change whether they stick to you. You absorb their energy. They push your electrons and protons. Or they reflect. And how you reflect them decides how it can affect something else. Things can see the pattern if you make a specific pattern. So you can understand magnets perfectly now, because magnets aren't making a force. They're just taking the force that comes in and they're creating its leaving with a pattern other magnets can see. And that's all we're really talking about, is the pattern is either visible or invisible. The fact is, the same amount of light was hitting those places that got no signal. The same amount of photons were hitting there. It's just that the pattern couldn't be turned into an electrical signal, and therefore we can't see it or detect it, because it won't make electricity.
Our last experiment is in the radio wave part of the spectrum.
So it's essentially the same experiment, you're just doing it now because you've taken, you started with photons, very tiny thing, you went to a microwave, and now you're going to go to a radio wave. So now you're going to go to something that could have a wavelength in feet or yards.
Here we will work at a frequency of 140 million cycles per second, corresponding to a wavelength of about 2.1 meters.
So it's 2 meters compared to the 3 centimeters. So again, more than 1,000,000 times bigger.
Because of this large wavelength, we obviously have to work with much larger physical...
It's not 1,000,000. It's a lot, but yeah, 3 centimeters into 100 centimeters, 200 centimeters. Yeah, it's 100 times bigger.
...apparatus and in a larger area.
So same idea. There's no slits here, and there's only 2 sources. So they've broken the whole idea of the double slit making the complex pattern. There's no complex pattern. There's no envelope pattern. None of the characteristics of a double source experiment, so to speak, are there, because the 2 slit experiment, again, is really the 4 source experiment because of the surfaces. There's no surfaces here. The photons aren't being broken, and you're not sending pieces. All you're doing is jamming the signal. The radio receiver, just like the klystron, it can't choose between 2 competing frequencies. If there's 2 frequencies hitting it out of phase, it can't choose one or the other, unless you made it a directional antenna and excluded one. But if it can receive both, it can't receive either. if they're out of phase.
This large field will be perfect for our experiment. Aside from the larger equipment which we'll use and the lower frequency, this experiment will be identical to the one you saw with microwaves.
So again, it's really not identical, but whatever, blah, blah, blah. But at least their two are consistent. So the microwave and the radio wave are really jamming experiments where the photon is analyzing fringes created by diffracted photons, scattered bits of a photon, to be more precise.
There are two antennas set up about 20 feet apart, which in this experiment will take the place of the two horns in the microwave experiment. The antennas are fed from the same transmitter, thus making...
So this is different than the microwave because, again, see, the problem with the Klystroms is it's hard to get them to go on and off in sequence with each other. That's why the signal had to be, put through a bunch of chambers to get the signal to go out. It had to be steered. But here you can just do it with the radio because you can have the same exact length of wire between the transmitter and the two antennas. So as long as the wire is exactly the same length, the stimulus to the antenna will be exactly the same. They'll both be in phase.
Them coherent sources of electromagnetic waves. We're going to pick up the resultant electric field from the two antennas with a similar one here. The way the waves come out from these two sources is just the way the klystron antenna sent out microwaves.
So again, it's not a wave, okay? It's reflected energy. The surface is vibrating. As the surface electrons vibrate, push in and out, they reflect the world and they change the signal the world sees because of how they're vibrating. But there's no wave. They're just pieces of little discrete pieces of energy reflecting off of electrons.
What we're doing is to pump electric charge from the transmitter into and out of the antennas and back and forth at the rate of 140 million times per second. It is this acceleration.
And so the electrons literally are just doing that at that incredibly high frequency. This is all the electrons are doing. It's going out and in, out and in, out and in. All you're doing is pushing on the atoms. When the electron pushes, it squeezes the atom. The electrons on the outside pop out, and then the next atom gets squoze, and the next atom gets squoze, and the next atom gets squoze, and it's pushing the electron out, giving it an acceleration. And that's all that's happening. And then it goes back to its original condition, squeezed back, squeeze back, squeeze back.
Charge which sends our electromagnetic waves off. Now, for ideas of the...
Literally, the universe is that simple. That there's just electrons. And again, they can absorb a piece of energy and move and gain momentum. Or if they're moving and the force is coming against them, they'll reflect it. And that's all you're seeing. You're just seeing reflections. You're just seeing a reflection off of me. I didn't produce any energy. Okay, the energy is coming from the external world, hits me, and then my surface creates the image you see.
Interference of electromagnetic waves are correct. We'd expect to find regions of constructive and destructive interference in the space here in front of the...
So again, there won't be any constructive and destructive per se. There's just going to be jam the signal, don't jam the signal. Jam the signal, don't jam. That means in phase, out of phase, in phase, out of phase. Nothing is constructing, and certainly nothing's destroyed. Again, the radio receiver is still getting hit by the signal. Okay, when they're out of phase, right? All the signal, all the energy is still hitting, and all the energy is still hitting the other side. So the energy hasn't in any way been destroyed. It's just that the receiver can't convert it into an electrical signal. because it's out of phase. The swing set can't be moved because there's somebody pushing the kid this way. At the same time, there's somebody pushing the kid that way. So it won't work.
Two sources. So what we're going to do is to move our pickup antenna back and forth in space, thus sampling the resultant electric field from the two sources.
So again, I have to emphasize, they could have done the experiment by having one antenna, transmitting them from here, and another antenna transmitting from opposite directions, and then put the pickup one in between, and they could do exactly the same experiment. So there'd be no capacity for the two signals to cross each other and interfere. So interference wouldn't be a possibility. One signal's coming this way, the other signal's coming this way. They never interact until they hit the source, demonstrating this isn't about interfering waves. It's about phase.
We'll convert the received signal into sound on this loudspeaker and also into a deflection on the meter. The reason you can hear the sound...
So again, it's all usually about electricity. That's what all this stuff does. It causes an electrical stimulus, and that's what we call a photon. And your brain's doing the same thing right now. It's receiving photons and turning them into electricity. And the ones that are not in the right pattern to make electricity, it can't see.
Is because we're chopping the transmitter signal 1,000 times per second. Now let's try the experiment.
So it should be understood that a signal comes in, 1,000 little wobbles happen, and they only show you the one wobble. That's the sound. Come on.
As we roll along, moving the detector, once again, we go through a series of minima.
So because of these huge distances, there's no central maxima. There's no overlap of the signal because the sources are so far apart.
Maxima. And minima. Now let's try it again.
What if your smile could
why?
go from looking like this
Yeah, why try it
to
again?
this?
Yeah, I should download these videos. So again, I just point out, you could do exactly the same experiment, just put the antenna in between the two sources and same effect. Meaning no crossover, no wave interference.
And I'll stop at a minimum. To see that this is really an interference effect, let's disconnect one of the antennas.
So same thing as covering one of the dishes. And again, so both signals are hitting the antenna. They're just out of phase. So the antenna can't receive either one. It's got two competing, it has to start wobbling on one of them. And they're both off in terms of how they're saying when to start. So the receiver just can't see either one. And as soon as you get rid of the jamming signal, obviously you can still, now you can hear the other one because it's not being jammed. So again, at the swing set example, right, if I got two people pushing at the same time, yeah, nothing happens. But if I just remove one of the people, now somebody can push, no problem. You can oscillate the swing.
John, you see the intensity has gone up, both on the meter and in the sound level. This is because we've disconnected one antenna, and so it can no longer cancel the field due to the other.
So it's just jam is what you should say. We've taken away the jamming signal.
Let's reconnect it.
Now we're jamming.
Our intensity is down again. We're at a minimum or a point of destructive interference. Let's try the same thing at a maximum.
So now they're in phase, so
And
no
let's
problem.
disconnect one of the antennas. Now you see the signal has dropped. This is because we removed an antenna.
Right, so you had two sources, twice the signal. Now you don't have twice the signal anymore because you only have one antenna. So again, too obvious.
So we're receiving the field due to only one, and so we get a smaller signal.
So if I had the two radio stations, competing radio stations, let's say they were playing exactly the same song at exactly the same time. And so you could sort of understand that, yeah, well, if they're both in phase, that if I'm at the same distance from both radio stations, the song will play just fine, be twice as loud, kind of thing. I get twice as much signal. And I can turn one of them off, and I still got half the signal. No problem. So it's, not complicated.
So you see, once again we have wave interference.
So it's not wave interference, it's signal jamming. It's pattern jamming.
This time in the radio wave region of the electromagnetic spectrum. There's one more wave property I want to show you, and that is that radio waves are polarized. The waves being transmitted...
So this is just antenna polarization. The signal goes the length of the antenna. That takes time. That's creating the polarization.
...by our antennas are polarized such that the electric disturbance is parallel to the metal rod or antenna. This is because we're pumping charge or accelerating it back and forth along the rod.
So the charges aren't accelerating that way and that way, up and down the antenna. No, the antenna is producing them out of its side, okay, in sequence.
And it is this accelerated charge which starts the wave going parallel to the rod. We can show the polarization of these waves as actually received by rotating the antenna. John, would you rotate?
So you're just going to turn an antenna this way, and you don't receive any signal because now most of the signal is going to miss you and you just have that little tiny center that's going to get hit. But the rest of your antenna is not going to get hit with any signal because it's not in line with the plane that the signal is being created on.
Rotated by 90 degrees. You see, as he rotates it, the intensity drops, and at 90 degrees, it has gone down to 0. This is because the antenna is now sending a radio wave polarized such that the electric field is perpendicular to the antenna that is receiving it.
So the whole way they are thinking of it going this way and this way, up and down the antenna, that's not what's coming out of the antenna. It's coming out of the antenna, the base first to the top, the base first to the top. So it's a line like this coming out of the antenna. So you have the antenna this way and the signals coming out this way.
They are perpendicular, you get a minimum received signal. Let's rotate it by another 90 degrees and see what happens.
Duh.
You see, the intensity has gone up again. This is because the two antennas are again parallel. The wave being transmitted is polarized such that it arrives at the receiving antenna with its electric disturbance parallel to the antenna.
The pattern, okay, being the reflection being created, obviously has a length to it. Alright. And so if I try to receive it this way, there's only one little tiny place where those two lines intersect. So obviously I can't see the pattern.
And is now fully received. Let's see what we have accomplished. By doing a simple interference experiment in 4 widely separated regions of the electromagnetic spectrum, I've been able to show you that the interference effects arise from waves.
So it's not interference. It's, in the case of photons, just break them, remake them. And the polarizing film proves you can remake them. And all the other experiments are just jamming. Just demonstrating the limitation of our receiving technology, that we're dependent on the receiving technology causing something, an oscillator, to oscillate. If the oscillator can't oscillate because there's too much noise, then you can't receive the signal.
That the waves are transverse and can be polarized. That they arise from accelerated charges.
Well, that's the only part that's true, okay, is that the movement of electrons changes the pattern, the viewable world. The moon's existence moving around the Earth would change how the Earth looks from someplace in space.
And travel with the speed of light. It is due to these common properties that we believe in the unity of the electromagnetic spectrum.
So there's no point in saying the unity of the electromagnetic spectrum when you believe in a woo-averse where these things are all magical, and now they even have ESP now. Back in the 60s, they didn't talk much about entanglement and all that mush. But that's what they've turned it into. It's a bunch of photons aren't where they are, they don't have a direction, they don't know where they're going everywhere in the universe and then deciding to land in one place. I mean, all the wooey crap it's turned into. And all you need to do is start with a false premise that this is a wave phenomenon, when no, it's particles that are in patterns. And such. So anyway, so there's another video like this that I do want to get to, because it has some other interesting experiments in it. So I'll probably be doing that shortly and such. So till the next time, blah 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 blah. Yeah, it's like I said, this wave particle duality only exists because they won't spend more than 10 minutes contemplating particle theories. They just have no interest in a rational, mechanical description of reality, because physics is just a wooey religion. Sorry, it's all it is.